All right, page 48, doing the associative, commutative, and distributive laws. Let's get some vocabulary first. A mathematical term is a number or a variable, or numbers and variables multiplied together. Terms are separated by mathematical operations, maybe adding, subtracting. So some examples of a term: 5, that's a term, it's a number. X, that's a variable. 5x, number times a variable. Could be even more complicated. It could be like 2 times the square root of 3 over 5 times x y cubed. That's still one term because there are no plus or minus signs in there. A variable is usually a letter, but it could be another symbol. I had a professor who liked to use smiley faces, and we had cyclops smiley and double smiley and so on. That was the variable scheme we used. So usually a letter to represent a quantity that can change. We often use X and Y, but we could use any letter. Notice that if we use like an L, we don't write it like that because that looks like a 1. We'll do a cursive L. Similarly, we don't usually use O because that looks like 0. But any letter can be used. Okay, a constant is a quantity that does not change. Often it's a number, like 5, or square root of 3 over 2, or negative 1.45 with the 5 repeating. Those are all constants. We could also have something like pi, which we talked about previously. Pi is a constant, 3.14 dot dot dot. And then a coefficient is a constant term multiplied by a variable, or maybe multiple variables. So 2x, 2 is the coefficient. Let's see. Actually, let's make this a little more clear. Let's go with 5x squared plus 2x plus 4. Which of these are coefficients? I want you to take a minute, think about it. Which of these are constant terms multiplied by a variable or variables? Pause the video if you need to. Okay, so this 5 is multiplied by a variable or variables. This 2 is multiplied by a variable or variables. This 4 is not. It is not a coefficient, even though it's a constant. Let's look at one more. Negative x plus 7. So negative x plus 7. Well, 7 is not a coefficient. It's not multiplied by a variable. But what about here? We have just a negative sign. We can't have just a negative sign, right? But what number can we always put in front of a variable? We can always put 1. So negative 1 is our coefficient. Negative 1. An expression is a mathematical phrase that we make with operations, numbers, variables. It never has an equal sign. It does not contain an equal sign. So some examples of expressions: 2 plus 4, that's an expression, or 5x plus 1/2, or negative 9 minus 6. Those are all expressions, just partial ideas, phrases. And an equation is kind of like a sentence. It's a complete idea. And an equal sign. It always has an equal sign. So some examples of equations would be, let's see, how about 2 plus 4 equals 6? That's an equation. Or 5x plus 1/2 equals negative 2y cubed. That's an equation. I can't solve it. I don't have enough information, but it is an equation. Then like terms, they have the same variables and exponents, and we can combine them together. Notice that they do not need the same coefficient to be like terms. So some examples of like terms are 2x and 5x. I can combine those to get 7x. 2xy plus xy minus negative 3xy. Those are all like terms because they all have an x and a y. Let's do one more example. Let's do 4x squared y plus 2x squared y. Notice that the variables match and the exponents attached to each variable match. So a non-example, we can take this and just break it slightly. Why is this not an example? Take a moment and pause the video if you need. Why is this a non-example when this worked? Well, it's because the squared is on x squared here, it's on y squared here. So those are not like terms. Another example, 2 plus x, it does not equal 2x, right? It's just 2 plus x, whatever that is. It might be the same as 2x coincidentally, but in general, this statement is not true. And similarly, 2x plus 3x to the fifth. Those are not like terms because they have the same variable, but they're to different exponents. Okay, we have a few conventions or rules that we normally follow when writing things. We put coefficients before variables. So 3x, negative 15 halves y cubed. And one reason we do that is because if I write something like that, it's hard to tell if I mean x cubed or if I mean x times 3. If I write 3x, I guess theoretically I could mean 3 times x, or I could mean 3 to the x power, but it's a lot more clear because the variables are often kind of lower down. We've got two special cases. 1x, I normally just write x, and 0x is just 0. I usually don't even need to write it. We write our variables in alphabetical order. So I have 1/2 a squared b. I have 3lw cubed. Those are all in alphabetical order by the letters. It doesn't matter what the exponents are. Now when we go down to number 3, though, we take a look at our exponents. We want them with exponents in descending order. So for example, we have 5x squared plus 2x minus 4. Okay, descending order of what? Well, of exponent. Here's a 2. X without an exponent is saying how many x's do I have? Well, I have 1. That's 1 is the exponent, 2, then 1. And because a non-zero number to the 0 power is 1, I could call this x to the 0. 2, 1, 0. Another possibility, we might have x cubed plus 5x squared y plus 2xy squared minus y z. There we go. So you'll see I look at the first variable alphabetically, that's x. I look at the numbers. And I have 3, 2, 1, 0. Now sometimes I'm missing numbers. I might have 5x to the 5th minus x cubed plus 6x. That's okay. I still have it in the right order because I have a 5, then it goes down to a 3, it goes down to a 1. Never go back up. If I had x to the 4th here, I would scoot that before the x cubed. Okay, so the way that I think about this is just remembering that it's kind of like dictionary order, right? If I have x cubed, that's x, x, x. If I have x squared y, that's x, x, y. X, x, x comes before x, x, y in the dictionary. The only thing you have to be careful of is remembering that if you have just an x, that actually comes after 2 x's or 3 x's or 4 x's or 5 x's. But if you're looking at different letter combinations, think about the dictionary. Okay.